Hello world, my name is Nikita Black, and I'm happy to see you on my channel. Today we will take another step toward our final goal. We will learn a lot of new things, create several important Vulkan objects, and understand how everything works under the hood. First, we will finally cover descriptor sets and descriptors. This will teach us how resources can be accessed from shaders. Next, we will create a pipeline. This is one of the fundamental objects in Vulkan, and it is absolutely required for any kind of rendering and even compute operations. And finally, we will draw our full-screen triangle on the screen. Along the way, of course, we will also solve plenty of errors and warnings, the usual stuff you have already seen in previous videos. So, prepare yourself a coffee, just like I did, and let's start coding. So we have a resource that we want to use on a shader, but how do we do this in Vulkan? In Vulkan, we work with so-called descriptors. A descriptor is a small container that holds information about an underlying resource. There are multiple types of descriptors. For example, buffer descriptors and image descriptors. They differ in the information they contain, but the core idea is the same. As Vulkan users, we do not know how descriptors are implemented internally. For us, they are essentially a black box that we use to communicate our intentions to Vulkan. Descriptors are a surprisingly complex topic. There is a very good article on the subject. But they are complicated from an implementation perspective, because different GPU architectures handle resource access differently. Luckily for us, as Vulkan API users, descriptors are fairly straightforward to work with. I created a small diagram to illustrate the idea. Here we have a GPU memory. Inside that memory, we store resources. When we want to access a resource from a shader, we provide a descriptor. In the image 0 example, you can see that the descriptor points to the memory associated with that particular image. It may also contain additional metadata such as image dimensions, format, or other information. Again, we do not know exactly how descriptors are represented internally. Different drivers may implement them differently. Vulkan abstracts all of that away from us. Another important thing is that we do not use descriptors individually in shaders. Instead, descriptors are organized into descriptor sets. Why is it done this way? There are several reasons. One of them is that updating a descriptor set has a cost. In Vulkan, we do not update descriptors individually. Instead, we update an entire descriptor set. Because of this, it makes sense to organize descriptor sets according to how frequently they change. For example, you might have a descriptor set that is updated only once during the entire lifetime of the application. You might have another descriptor set that is updated once per frame. A good example would be a buffer containing the current frame number or camera data. You could also have a descriptor set that is updated for every draw call. That is the main idea. Group resources according to how often they need to be updated. In my opinion, the concept is quite straightforward. As usual, Vulkan does not allow an unlimited number of descriptors or descriptor sets. There are limits, as well as minimum guarantees defined by the specification. For descriptors, the limits are generally very high, often thousands of descriptors. The number of descriptor sets depends on the hardware. Vulkan only guarantees support for at least 4 descriptor sets. These are limits reported by my hardware. As you can see, I can have up to 32 descriptor sets bound simultaneously. We can also see that the available descriptor counts are quite large. So far so good. Here is an example of how descriptors and descriptor sets are used in a shader. I took the shader from the official Vulkan samples. We can see that the vertex shader uses a uniform buffer. The descriptor is bound to set 0, binding 0. The fragment shader uses the same set 0, but binding 1 for another descriptor. The important thing to understand is that descriptor sets are bound per pipeline, not per shader. If a pipeline contains a vertex shader, fragment shader, tessellation shader, or any other stages, all of them share the same descriptor set layout. For example, we cannot use set 0 binding 0 for a different resource in the fragment shader, because that slot is already occupied by uniform buffer used by the vertex shader. This is how Vulkan has worked since version 1.0. I like to think about descriptor sets in the same way I think about the function declaration in C++. When we declare a function in C++, we specify the arguments that the function expects. For example, std_sort expects a range of iterators and optionally a comparison function. At runtime, we provide different iterators and different comparison functions, but function signature itself remains the same. The idea here is very similar. We declare that a particular binding contains a buffer, an image, or some other resource type. Later, at runtime, we provide the actual resource that should be used by the shader. Pretty straightforward, right? So, if this works so well, why do we need other approaches? The first issue is how descriptor sets are provided to a pipeline. We do not provide sets and bindings directly. Instead, we create a so-called pipeline layout. This pipeline layout is essentially the signature I just mentioned. As you can imagine, different shaders often require different signatures. For example, a sky shader may use one set of resources, while a terrain shader may use completely different set. In this example, the terrain shader doesn't use any bindings at all. As a result, different shaders often require different pipeline layouts, which means different pipelines. This can become annoying when you have a large number of shaders. It also makes shader iteration more cumbersome. Every time you change resource a shader uses, you may also need to update the pipeline layout. More importantly, the pipeline layout is required when creating a graphics pipeline, as we will see later today. Pipeline creation is not particularly fast operation. In the end, all it becomes a maintenance problem. For a small application with only a few shaders, this may be perfectly fine. For a larger application, it can become difficult to manage. There are also situations where you do not know in advance which resources a shader will need. For example, imagine a shader that can access an arbitrary number of textures. You may not know ahead of time how many textures will be available. You could use a texture array in this case, but that requires all textures to have compatible dimensions and formats, which is not always practical. To address these limitations, several proposals were introduced over the years. One of them is descriptor indexing. Descriptor indexing started as a Vulkan extension and later became part of the core Vulkan specification. With descriptor indexing, we treat descriptors as arrays. Inside the shader, we do not care how many elements the array contains. Of course, on the Vulkan side, we still have to allocate a certain amount of space for the array, but from the shader's perspective, it behaves like a regular array that can be indexed dynamically at runtime. Looking a bit ahead, here is a shader we will later use for the GUI. You can see that the vertex buffer is exposed as an array of descriptors. When we want to access a particular buffer, we provide its index through a push constant and access it just like a normal array element. This approach solves many problems. For us, one of the biggest advantages is that we can create a single pipeline layout, in other words, a single signature, for all shaders. Our layout will contain storage buffers in set 0 and images in set 1. You can mostly ignore the binding numbers for now, because they are not particularly important to understand the concept. Briefly, we could have a few descriptors at the beginning of a set, and then a descriptor array as the last binding. The idea is very similar to variadic parameters in C++ function declaration. The variable length part comes last. We will see how this is implemented in code, and it will become much clearer. I also want to mention that even more modern approaches to descriptor management exist. For example, there is an extension that introduces descriptor heaps. With this approach, descriptors can be accessed more directly, significantly reducing the importance of traditional descriptor set and pipeline layouts. However, I already have working code based on descriptor indexing, and it is very likely to run on your hardware as well. The newer approaches are still relatively recent at the time of recording and support varies across drivers and hardware vendors. For that reason, descriptor indexing has a very good middle ground. It provides most of the flexibility we want while still being widely supported. To create a descriptor set, we first need a descriptor pool. A descriptor pool contains a certain number of descriptor sets, and whenever we add a new descriptor set, we allocate it from that pool. The next step is to create a descriptor pool itself, define a descriptor set layout, and implement a function that allocates descriptor sets. Inside these functions, I will perform all the necessary validation and error checks. As usual, let's write some code first, and then I'll explain how everything works. First, let's see how we create a descriptor set layout. As I mentioned before, and I'll repeat once again, in this application, we will use only two descriptor types: storage descriptors and combined image sampler descriptors. This function creates the descriptor set layout for either of these descriptor types. In our case, each descriptor set contains only a single binding. However, that binding is not a single descriptor. It is an array of descriptors of the same type. Let's see how this works. First, we define the binding structure. Here we specify that the descriptor set has only one binding, meaning only one binding slot. This field specifies the binding number, so we bind it to index 0 within the descriptor set. Next, we specify the descriptor type, which is either a storage or a combined image sampler descriptor. Then comes the descriptor count. Right now, it is set to 0 because we do not yet know how many descriptors the hardware supports. We first need to acquire that information, and we will do that later in this function. The stage flags specify that this descriptor set layout can be accessed from all shader stages. Finally, we ignore immutable samplers because we do not use them in this application. Next, we fill out the create infrastructure. Here we provide the binding we just created along with a few flags. The interesting part is this additional flag structure. As you can see, we define only a single binding flag because our descriptor set has only one binding. If we had multiple bindings, we would have to provide a binding flag for each one. Now let's look at the binding flags themselves. The first one, variable descriptor count, allows us to use a variable-sized descriptors array. That is exactly the feature we need. The second flag, partially bound, allows some elements of the descriptor array to remain unbound. For example, we could bind descriptor 0 and descriptor 3, while leaving descriptors 1 and 2 unused. Without this flag, the validation layers would complain because every descriptor in the array would have to be bound. The third flag, update after bind, allows us to update descriptors after they have already been bound to the pipeline. Without this flag, we would first have to populate every descriptor and only then bind the descriptor set. Updating a descriptor simply means specifying which resource it refers to. For example, the memory location, size, image view, sampler, and so on. With this flag enabled, we can bind the descriptor set first and update individual descriptors later. This is especially useful when working with variable-sized descriptors arrays because we often do not know in advance how many descriptors we will actually need. The create info itself also has update after bind flag, but this flag refers to the descriptor set, not a descriptor. Yes, this looks like a redundant thing to specify twice, but we have to do this. Next, we use the create info to query whether this type of descriptor layout is supported. We pass the create info to get descriptor set layout support function. We also provide a support structure that will be filled by that function. The structure contains a supported field, which tells us whether this layout is valid. Naturally, we expect this value to be true. Another structure, which we pass through the pnext chain, contains information about variable descriptor counts. This tells us the maximum number of descriptors supported for this type of layout. After calling this function, we first verify that the layout itself is supported. Then we check whether the number of descriptors we want to use fits within the supported limit. This function receives the desired descriptor count as a parameter. I have not yet decided on the exact number. I will probably use a fixed value, something like 100 descriptors, but we will see. If the requested descriptor count is supported, we continue. Otherwise, there is nothing we can do except report an error. Finally, we update the binding. We replace the initial descriptor count of 0 with the actual number of descriptors we want to allocate. Then we reuse the same create infrastructure to create the descriptor set layout. And that's it. Now let's move on to the next function. Let's look at the create descriptor pool function. For now, we create only one descriptor pool. However, in practice, we will need multiple pools because descriptors, much like command buffers, are frame resources. When we submit a frame to the GPU, its descriptor sets may still be in use. When we start recording the next frame, we cannot immediately reuse those same descriptor sets because we do not know whether the GPU has finished processing the previous frame. This is exactly the same problem we already solved for other per frame resources. That is why we create one descriptor pool per frame in flight. In our case, we have 2 frames in flight, so we will have 2 descriptor pools. At the beginning of each frame, the first thing we do is reset the corresponding descriptor pool. As you remember, this is completely safe, because our synchronization guarantees that the previous frame using the same frame index, either 0 or 1, has already finished executing on the GPU. Now let's look at the pool creation info. Here we use the same update after bind flag that we enabled for the descriptor set layout. This is required because descriptor pools must also support descriptor sets created with this flag. Next comes max sets. Looking at it now, I think this value is actually wrong. It should probably be set to 2. The reason is that in our application we will bind only 2 descriptor sets for the entire duration of the frame. I will draw a diagram later because I think it makes the idea much easier to understand visually. But the basic idea is this. At the beginning of the frame, we bind our 2 descriptor sets. Each descriptor set contains an array of descriptors. Whether a shader needs a resource, it simply uses one of the available slots in these arrays. For example, the first draw call might use descriptor slots 0, 1, and 2 because it needs free buffers. The next draw call would then use slots 3, 4, 5, and so on. The important point is that all shaders share the same descriptor set layout. This greatly simplifies the system because we no longer need different layouts for different shaders. Thinking about it now, if max sets should be 2, then the pool sizes probably need to be updated as well. The reason I originally used max sets equal to 1 is that my first idea was to have a separate descriptor pool for each descriptor type. For example, we would have one pair of pools for storage descriptors, one pool per frame in flight, and another pair for combined image samplers. But after thinking about it, I don't see much benefit in doing that. It is much simpler to keep both descriptor sets in a single descriptor pool. So let me quickly fix that. Here it is. I now specify 2 different pool sizes, one for the storage descriptors and one for combined image sampler descriptors. Then I pass this information to the create infrastructure. I also set the maximum number of descriptor sets to 2. After that, we simply call the Vulkan function to create the descriptor pool. Nothing particularly interesting here. Now let's move on to the next function. In this function, we allocate a descriptor set. We provide the descriptor pool, the descriptor set layout, and the number of descriptors. Since I wanted to keep everything simple, this function is also very straightforward. All of this information is placed into the allocation infrastructure, and then we simply call the Vulkan allocation function. One thing you should pay attention to is the descriptor count. Obviously, this number must be less than or equal to the number of descriptors you reserved when creating a descriptor pool. If you ever need more descriptors than the pool provides, you can simply create another pool. In another project, I use a more sophisticated system that creates new descriptor pools on demand and allocates from them dynamically. However, I did not want to introduce that complexity into this application. Here I can safely assume that 100 descriptors will be enough. Even if that turns out not to be the case, increasing the limit to 200 or even 1000 is trivial. I just wanted to mention that, so you know there are other approaches. Now that these helper functions are ready, we can integrate them into the graphics manager and see how they are used during rendering. As first step, I added 3 new fields: descriptor pools, a storage descriptor set layout, and a combined image sampler descriptor set layout. The combined image sampler descriptor combines an image descriptor and a sampler descriptor into a single descriptor type, which I find very convenient. Let's see how we create these objects. We create them during initialization. Here I call create descriptor pool twice, once for each frame in flight. I also create 2 different descriptor set layouts, one for each descriptor type we are going to use. That's it. Of course, I also make sure to destroy everything during cleanup. In destroy device, we destroy all of these objects. So far so good. If you compile the project, everything builds successfully. However, if you run the application, we immediately see several validation warnings. Let's take the first warning and read it carefully. It says that required feature is not enabled. In fact, it reports that several descriptor indexing features are missing. And indeed, if we look at our Vulkan 1.2 feature structure, we can see that all the descriptor indexing features are currently commented out. If we uncomment them, recompile, and run the application again, we get another warning. This time the problem is that I enabled the wrong feature. Instead of storage image, we actually need sampled image. Let's fix that, rebuild the project, and run it again. Now the validation layers are happy, and there are no more warnings. Beautiful. The next step is to reset the descriptor pools and allocate fresh descriptor sets at the beginning of every frame. Let's implement it now. That's it. In the start frame function, we do essentially the same thing as before. First, we obtain the descriptor pool corresponding to the current frame index. Then we use this pool to allocate 2 descriptor sets. For now, I marked these descriptor sets as maybe unused, otherwise the compiler would warn that they are allocated but never used. The next step is to decide how we want to use these descriptor sets throughout the frame. I suggest storing this temporary per frame data in a dedicated frame data structure and keeping it as a member of a graphics manager. Later, whenever we need access to this data, the rest of the code can simply query the current frame data and use its descriptor sets, command buffer, or any other per frame resource. I updated the code accordingly. Now, I allocate the descriptor sets and store them directly in the corresponding frame data instance. At this point, almost everything is in place. We can finally start updating these descriptor sets. Let's look once again at the shader we wrote for rendering the full screen triangle. The vertex shader doesn't use any resources. The fragment shader, however, uses an image descriptor. This descriptor is located in descriptor set 1, with the descriptor array bound to binding 0. So here's what we need to do. At the beginning of each frame, we bind our descriptor sets. Then we update the descriptors we actually need. For the full screen triangle, we only need to update the image descriptor. Once that's done, the shader can finally access our render target. Let's implement it now. I added a new field to frame data for the command buffer, and I moved the code that resets the command pool and allocates a new command buffer from end frame to start frame. This change is necessary because we need a command buffer in order to bind descriptor sets. Next, I use this command buffer together with our newly allocated descriptor sets to bind them to the pipeline. However, as you can see, the Vulkan bind descriptor sets function requires a pipeline layout. So what is a pipeline layout? Isn't a descriptor set layout enough? No, it isn't. Earlier, I compared a descriptor set layout to a C++ function signature, where different resources are bound to different slots, just like function parameters. You can think of a pipeline layout in a similar way, except that instead of individual resources, it uses descriptor sets themselves. In other words, you can create a descriptor set and reuse it with different shaders. But for an entire graphics pipeline, including the vertex shader, fragment shader, and any other stages, you must define a single pipeline layout. This pipeline layout specifies which descriptor sets are available to the pipeline, along with additional information such as push constant ranges. We will see what that means shortly. So, our next step is to create this pipeline layout. Here's how we create the pipeline layout. First, we define a push constant range. What are push constants? They are simply a convenient way to pass a small amount of data directed to shaders. This data is copied into the command buffer, and the shader can access it during the execution. The downside is that push constants are very limited in size. Here I set the size to 128 bytes. Why 128? Because for Vulkan versions earlier than 1.4, the specification guarantees at least 128 bytes of push constant storage. Starting with Vulkan 1.4, the guaranteed minimum increases to 256 bytes. Since we are targeting Vulkan 1.3, we stick with 128 bytes. This is not much. For example, a 4x4 matrix occupies 64 bytes, so 128 bytes is enough for only 2 matrices. If you need to pass more data than that, you should use a buffer instead, for example a storage buffer, which we already use. In our application, however, we will mostly use push constants to pass descriptor indices, just as you saw in the shaders. We will see many more examples of this later. Next come our descriptor set layouts. Since all of our shaders will use only 2 descriptor sets, we can create a single pipeline layout that works for every pipeline in the application. This is an important advantage. Without descriptor indexing, different pipelines usually require different resource layouts, so you have to create separate pipeline layouts. For example, we will have a full-screen triangle pipeline, an EM-GUI pipeline, and a mesh shader pipeline for rendering the teapot. Without descriptor indexing, these three pipelines would all require different pipeline layouts because they use different resources. Of course, you could create some dummy resources in the shaders and simply never use them, but that quickly becomes messy. Descriptor indexing is widely supported today, so I think it is a much cleaner solution. As usual, we create the pipeline layout in the graphics manager initialization, and also we destroyed in destroy device function. Now let's see how we update a descriptor set. In other words, how we tell the GPU which resources the shader should use. Now let's look at the changes I made to the code. The first thing I did was replace the clearing of the swap chain image with the clearing of the render target. From now on, everything we render will go into the render target. So this is the image we want to clear at the beginning of every frame. I basically moved the code from compose rendering to render target rendering. The idea is simple. At the beginning of the frame, we attach the render target as the color attachment. From that point on, every fragment shader that outputs a color will write that color into the render target. In other words, every draw call between start frame and end frame will render into the render target. Let's look inside. Most of the code stayed exactly the same. The only thing I had to change was the barrier for the render target image. Since we now use this image both for rendering and for sampling, in other words, reading it in the fragment shader, we need to adjust the barrier accordingly. Let's start with the destination stage and access mask. At the beginning of the render pass, we want the image to be used as a color attachment. The only operation performed on it during rendering is writing. We also don't care about the previous contents of the image. As you remember, that means that the previous layout is effectively discarded during the transition. The old contents may be lost or remain implementation defined, but that doesn't matter because we overwrite the entire image every frame. The final layout at this stage is color attachment optimal. Later, when rendering is finished and we begin the compose pass, the render target will no longer be written to. Instead, it will be sampled by the full screen triangle shader. That means we transition it to a different layout, stage and access mask. The destination stage becomes the fragment shader stage because that's where the image will be sampled. The access mask changes from write to read because the fragment shader only reads from the image. So that is the only change. Everything else in this function stays exactly the same. Since I moved the rendering code out of begin compose rendering, I also had to update that function. The compose pass no longer clears the swap chain image because the full screen triangle completely covers it. Instead, the function now takes the render target as a parameter and only performs the layout transition for that image. The barrier is the counterpart to the one we just discussed. At this point, rendering into the render target is finished, and we are about to sample it while rendering the full screen triangle. So we transition the image from the color attachment stage to the fragment shader stage. The previous access was a write operation. The next access will be a read operation performed by the fragment shader. Finally, the image layout changes from color attachment optimal to shader read only optimal. That's it. Everything else remains exactly the same as before. Now comes the interesting part, the draw full screen triangle function. This is where we finally update the descriptors. As you remember, the full screen triangle doesn't use any vertex buffer. We simply draw 3 vertices and calculate their position dynamically in the vertex shader, so no vertex data is required. However, we do need our render target because the fragment shader will sample from it. For the shader to know where to read the image from, we have to update the descriptor set. In other words, we take a free slot in the descriptor array and write a descriptor that points to the actual image resource. Here we use our frame data. As you remember, at the beginning of the frame, we created a frame data object specifically for the current frame. It contains the comment buffer and our 2 descriptor sets, the storage descriptor set and the combined image sampler descriptor set. In this function, we are only interested in the combined image sampler descriptor set. We start by creating descriptor image infrastructure. Here we specify the render target sampler. We haven't created the sampler yet, that will be our next step, but we need to provide it here because we are using a combined image sampler descriptor. In other words, each descriptor contains both an image and a sampler. We could keep these things separate and, for example, use the same sampler with multiple images. For this application, however, it is simpler to combine them into a single descriptor. Next, we provide the render target image view and specify the layout the image should be in when the shader accesses it. Since we only sample from the render target, we want it to be in the shader read only optimal layout. Next, we create write descriptor set structure. Here, we specify which descriptor set we want to update. Since we are updating an image descriptor, we use our combined image sampler descriptor set. The destination binding is 0. This is the only binding we use in this application. As you remember, this binding contains an array of descriptors. In our case, the array has 100 image descriptors. The interesting part is the destination array element. Although the array has 100 elements, the shader still needs to know which slot contains the descriptor we want to use. To manage this, I added two new fields to frame data: a storage descriptor counter and an image descriptor counter. At the beginning of every frame, both counters are initialized to 0. Each time we allocate a slot in descriptor array, they use the current counter value and then increment it. So the very first image descriptor written during the frame goes into slot 0. If other shader later needs to update the same descriptor set, it uses slot 1, then slot 2 and so on. I'm talking about allocations within a single frame. Next, we specify that we are updating a single descriptor. The type is combined image sampler. Then we provide the image info we just created. The remaining fields are used in updating buffer descriptors instead of image descriptors. Vulkan uses the same write descriptor set structure for every descriptor type. The textile buffer view field is something we want to use. It allows Vulkan to treat a buffer as if it were an image inside the shader. Finally, we call the Vulkan function to update the descriptor set with all this information. All of this may sound confusing, but the core idea is actually quite simple. To make it easier to understand, I prepared this diagram. I think the visual representation makes the process much clearer. Here we have a complete frame. Looking a bit ahead, these are the draw calls we will perform during a single frame. First, we draw the T-pod. Then we render the UI. Finally, we draw the full-screen triangle that copies the render target to the swapchain image. After that, we submit the command buffer. Let's start with the T-pod. The only resource it needs is a buffer containing the control points. So we place that buffer into slot 0 of the storage descriptor array. Next comes imGUI. This shader needs two different resources. It needs a storage buffer containing the vertex data, and it also needs an image for the font texture. That means it uses both descriptor sets. Since storage descriptor slot 0 is already occupied by the T-pod's control point buffer, we obviously can't reuse it. Instead, we increment the storage descriptor counter, and the vertex buffer goes into slot 1 of the storage descriptor array. The font texture, however, uses the image descriptor set. Since no image descriptors have been allocated yet during this frame, it goes into slot 0 of the image descriptor array. After rendering the UI, we move on to the full-screen triangle. This shader only needs an image. It doesn't use any storage buffers. Again, slot 0 of the image descriptor array is already occupied by the font texture, so we allocate the next available slot. The render target descriptor is therefore written into slot 1, pointing to the render target image. After that, we submit the command buffer and start the next frame. At the beginning of the next frame, the whole process repeats. As you remember, however, we now use a different set of per-frame descriptor sets, so we never override descriptors that the GPU might still be using. After 2 frames, we wrap around to the first descriptor sets again, and the cycle repeats for every subsequent frame. Now let's create the missing sampler. After that, I'll explain the code, and we can run the application to see whether we get any validation warnings or run into any other problems. One thing I forgot to mention. I moved the frame data struct into a separate header file. This is necessary to avoid including the entire Graphics Manager HPP everywhere. As you remember, frame data was originally nested inside Graphics Manager. Now back to our sampler. Our sampler is very simple. We don't use any special addressing modes or filtering. We don't use MIP mapping, and we don't rotate textured objects. So anisotropic filtering isn't needed either. Basically, I'm using the default parameters. They work perfectly for our use case, because all we need to do is map the render target to the swap chain image 1-to-1. Both images have the same dimensions, so we simply read the same number of pixels that we write. That's it. As usual, I create the sampler during initialization and destroy it in the destroy device function. Now let's compile the project and run it. Okay, we immediately get a few validation warnings. These warnings are actually related to descriptor indexing. The validation layer says that I'm trying to access a descriptor slot beyond the allocated range. In other words, beyond our 100 descriptors. This error is actually quite predictable. At the beginning of each frame, we create fresh per frame resources by allocating new descriptor sets and a new command buffer. However, we never reset the descriptor counters. Let's fix that. Now let's rebuild the project and run it again. This time there are no validation warnings, which means everything is working as expected. By the way, you won't see the green screen anymore. We no longer clear the swap chain image. We still present it, but we don't actually render the full screen triangle yet. We already have almost everything we need. We have descriptor sets, we have pipeline layout, we even have the shaders. The only missing is that we don't actually use those shaders anywhere. So the final step before we can draw the triangle is to create a graphics pipeline. What is a pipeline? Pipeline is the object that defines the GPU state used for subsequent draw calls. In OpenGL, we could change many GPU states independently at runtime. For example, we could switch shaders, enable or disable multisampling, and so on. In Vulkan, all of the states are grouped into a single pipeline object. As a result, the graphics pipeline is a fairly large object containing many different pieces of state. The idea is that the driver can validate and prepare everything when the pipeline is created. By using a pre-computed pipeline, the driver performs much less work during rendering, making execution more predictable and in many cases faster. That was essentially true when Vulkan 1.0 was introduced. Over time, Vulkan became more flexible, and many states that were originally fixed in the pipeline can now be changed dynamically at runtime, as we will see later. Even so, most of the rendering state is still defined by the pipeline object. Without further ado, let's create a pipeline and finally draw our triangle. By far, this is the longest function we have written. Just look at it, it's almost 200 lines of code. Let's start from the beginning and see what it does. Because of the amount of information here, I will focus only on the fields that really matter and are relevant to each pipeline state. I won't discuss fields that are left at their default values or are not used by a particular state. We start by getting our compiled shader binaries. As you remember, we compiled the shaders to SPIR-V and embedded them directly into the executable. We are using the CMaker C library for this. The way we retrieve these binary blobs from the executable is by using CMRC. We declare our resource, the library creates a virtual file system for us, and we simply request the file by name. This is the name we specified when we edit the shader. Now we have the compiled data. But to create a pipeline, we first need a Vulkan shader module. Here, I created another helper function because we will use it every time we create a new pipeline. The first thing to do is to perform a couple of sanity checks, that the shader exists and that the size is divisible by 4. That's important because the shader data is provided as bytes, but shader module createInfo expects a pointer of uint32 data. Many examples simply reinterpret cast the byte pointer, and although this usually works, in C++ that's actually undefined behavior. The rule is that you can cast any object to char or std byte, but you generally can't reinterpret an arbitrary sequence of bytes as another object type. The correct approach, at least in C++23 and earlier, is to use memcopy. Using memcopy is well defined, provided the destination tab is trivially copyable. Here, since we are copying into std vector, it's perfectly valid. We copy the byte data into the vector, where it is interpreted as uint32 values. Then we pass this data to createShaderModule function to create the Vulkan object. Finally, we use these two modules, the vertex shader module and the fragment shader module, to create the shader stage infos. Here they specify the stage for each module, provide the module itself, and specify the entry point name. In our shaders, the entry point is simply main. Everything else is left at its default value. The next state we need is the input assembler state. Here we tell the pipeline how the input data should be interpreted. For example, if you provide 3 vertices, the pipeline could interpret them as 3 points, a line strip, or a triangle. In our case, of course, we are interested in triangles, so we specify the triangle list topology. The next state is the rasterization state. Here, we are mainly interested in the polygon mode. Basically, should the GPU fill the triangles or render them in wireframe mode? For our full-screen triangle, we obviously want it to be filled. We also specified the cool mode, so the back face of the triangle will be culled. To determine which side is the front face and which is the back face, we need to specify the front face wind decoder. Here we use clockwise ordering. If you open the full-screen triangle vertex shader, you'll indeed see that our 3 vertices 0, 1 and 2 are defined in clockwise order. The next state is the color blend attachment state. This controls how the output color is blended with the color already stored in the render target. You're probably familiar with alpha blending, where they first draw a background and then blend a semi-transparent object on top of it. For our full-screen triangle, we obviously don't want any blending, because it is the only triangle on the screen and it should completely cover the render target. So I disable blending by setting this field to false. Everything else is left at its default value because once blending is disabled, the remaining blend parameters are ignored. We then use this attachment to create the color blend state. Again, only the attachment itself is important here. Everything else is left at its default values. The next state is the dynamic state. I mentioned before that the idea behind the pipeline is to define every possible GPU state, then the pipeline is created. But sometimes this isn't very convenient. For example, one of the important states is the viewport state, and the viewport depends on the window size. Of course, when we resize the window size changes. Without any special support, this would mean recreating the pipeline every time the window is resized. That's not very practical, because pipeline creation can be an expensive operation. There are ways to improve pipeline creation performance, but in general, it's still something you want to avoid. Vulkan has an answer to this. Some pipeline states can be marked as dynamic. That means we don't need to recreate the pipeline. We can simply change those states at runtime. Here we specify that we will use 2 dynamic states, the viewport and the skisser. there are many other dynamic states available. Some are supported out of the box, while others require specific Vulkan features to be enabled. Next, we create the dynamic state info and pass our list of dynamic states. Even though the viewport and skis are dynamic, the corresponding state structures still have to be provided when creating the pipeline. Otherwise, the validation layers will complain. So here I create a dummy viewport state, it will be overwritten later anyway. Next comes the multi-sample state. Again, we don't use multi-sampling in this application, so I set the sample count to 1, meaning 1 sample per fragment. Everything else is left at its default value. The next state is the vertex input state. You have probably heard the terms vertex buffer and index buffer. Normally, a vertex buffer stores vertex data, and each vertex contains attributes such as position, UV coordinates, and color. You then provide a description of how this data is laid out in memory, and the GPU automatically fetches the correct attributes and passes them to the vertex shader. We won't use this mechanism in our application. We will still use a vertex buffer, but we will treat it as a regular storage buffer. We will also use an index buffer, and in the shader, we will use the index to manually fetch the required vertex from the storage buffer. Because of that, we completely skip the vertex input state. Vulkan still requires us to provide it, but all the fields are simply left empty. And the next state is the depth stencil state. Again, since we are rendering only a single full-screen triangle, we don't need depth testing or stencil testing. So I disable both depth testing and stencil testing. The remaining parameters are irrelevant for us. Next comes the rendering info. In one of my earlier videos, I explained that the original Vulkan 1.0 required you to create a render pass and one or more subpasses. The render pass then had to be specified and created in the pipeline. This made pipeline management more complicated. For example, if the render pass changed, for instance after resizing the window, you often had to recreate the pipeline. Managing render passes and subpasses also added a fair amount of complexity. Over time, Vulkan introduced the dynamic rendering feature. With dynamic rendering, we no longer need render passes. Instead, we simply begin and end rendering at runtime, as you have already seen. That's the approach we are using here. To use dynamic rendering, we create a rendering infrastructure. Here we specify the number of color attachment, in our case just one, and the format of that attachment. For the full-screen triangle, this is the format of the swap chain image, where the final color will be written. The depth and stencil attachment formats are not relevant here. And finally, after defining all the states, we can create the pipeline. Here, we create the pipeline create info. The rendering info we discussed earlier is a relatively new feature that didn't exist in the initial Vulkan specification. That's why it is provided through the pnext pointer of the pipeline create info. I hope you remember how we use the init struct helper to conveniently set the pnext pointer. All other fields basically just references to the states we already defined. Here we specify that the render pass is null. The subpass field is not relevant in this case. What's interesting are these two fields, the base pipeline handle and the base pipeline index. The idea is that if we have multiple pipelines and they are similar, we can reuse an already existing pipeline when creating a new one. This can potentially improve pipeline creation performance. Also, if you look at the Vulkan function used to create pipelines, you will notice that it uses the plural form. It can create multiple pipelines at once. These two fields, the base pipeline handle and the base pipeline index, specify which pipeline should be used as the base pipeline. This pipeline is created first, and subsequent pipelines can use it as a starting point. This is not relevant for our application, so we leave these fields as null pointer and -1. Next, we call the Vulkan function to create the pipeline. After the pipeline is created, we can destroy the shader modules because we don't need them anymore. At this point, the driver has processed our SPIR-V code. As you know, SPIR-V is an intermediate representation designed to work across different vendors. However, every GPU vendor has its own low-level instruction set, so the driver compiles the SPIR-V code into the native GPU code for the specific hardware. That's why after this point the shader modules are no longer needed. Here I only added a to-do command because, for example, if pipeline creation fails, the shader modules will not be destroyed. But in our case, if pipeline creation fails, we are basically unable to continue. So we will terminate the application and the runtime will clean everything up for us. Still, this should be a good exercise to create a proper C++ wrapper with RAI that handles this automatically. With this function implemented, we can finally create our pipeline during initialization. And of course, we also need to destroy it in the destroy device function. Now, let's build the application, then let's run it. And as we can see, it runs perfectly. We don't see any validation layer warnings. You can also see that the Vulkan configurator is running. It's important not to forget to test the code with validation layers enabled. Excellent. At least we have successfully created the pipeline with all the required states. However, we still don't actually use it. To use the pipeline, we need to pass it to our draw full screen triangle function, where we will bind this pipeline. Let's try to edit this now and see what happens. Cool, so we have finally bound our pipeline to the graphics bind point. If you are curious, there are other bind points as well, such as compute bind point, the ray tracing bind point, and even some vendor-specific ones. But here we're just using the good old graphics bind point. With the GPU state configured and the descriptors updated, we can finally issue the draw command. Here, I record the draw command into our command buffer. I specify that we want to draw 3 vertices. The next parameter is the instance count. We don't use instancing, so we will draw only a single instance. In other words, one triangle. The next parameter specifies the first vertex index. For example, if you are using GL vertex index in the vertex shader, its initial value will be whatever we specify here. The last parameter is the first instance. Again, since we don't use instancing, we leave it at 0. Now we can build the application and finally run it. A lot of warnings. But if you followed it carefully when we created the pipeline, you should already know what the problem is. As you remember, we marked some states as dynamic. That means these states must be set at runtime, essentially once every frame, and we never actually did that. The validation layer very explicit here. They tell us exactly what's wrong. We never set our dynamic viewport and skisser states. Let's fix that now. I added 2 new Vulkan function calls to our draw full screen triangle function. First, I call setScissor, then I call setViewport. As usual, these functions take the command buffer first, then they take the first viewport or scissor, index, and the number of viewports or scissors to set. This is usable if, for example, we have multiple render targets or multiple color attachments bound to the pipeline. Since we are using only a single color attachment, one viewport and one scissor are all we need. Now that we have fixed this, let's build the application and run it. Here we see something interesting. Although we still get some validation layer warnings, the window has changed. Instead of black, it's now green. So something is definitely happening, but for some reason the validation layers are still complaining. Let's investigate what's going on. Again, we are quite lucky because the validation message is very explicit. It tells us that we declared a push constant range when we created the pipeline layout, but we never actually updated the push constants before using the draw call. So why did anything work at all? Why do we still get the correct color? If you look at the shader, we can see that the fragment shader expects the descriptor index of our render target inside an array of image descriptors. Earlier, we updated the descriptor set and specified that the destination array element is 0. In other words, the render target descriptor is written into slot 0 of descriptor set 1 binding 0. However, we never updated the push constant that tells the shader which descriptor slot to use. It just so happens that the push constant memory still exists because we reserved it when we created the pipeline layout. And by pure luck, the render target descriptor index happens to be initialized to 0. As a result, the shader reads descriptor 0, which is exactly where we placed our render target. This is pure luck. If we used any other descriptor slot, the code would stop working. We can easily verify that by changing the destination array from 0 to something else, for example 5. And now we get a black window, exactly as expected. This is one of the frustrating parts of graphics programming. Sometimes everything looks correct, but nothing works. Other times, like here, the code appears to work even though the validation layers are telling you that it isn't correct. So I think we have found the last missing piece of the puzzle. We need to update the push constants and pass the correct descriptor array index to the shader. Let's do that now. Let's see how we can push constants. At first I tried using the new pushConstants2 function. However, it turned out that this function isn't available in Vulkan 1.3, so it simply caused the segmentation fault. Because of that, I'm using the good old pushConstant instead. This function takes the command buffer and the pipeline layout. It needs the pipeline layout because that's where the pushConstant ranges are defined, so Vulkan can verify that the range we are updating is valid. Next, we specify the shader stages that will use these push constants. In our case, we make them available to all stages. Since push constants represent a range of memory, and we can update different parts of that range with multiple calls, we also need to specify an offset. In our case, we update the entire range at once, so the offset is 0. Then we specify the size of the push constant data, and finally, we provide the data itself. This function simply expects a binary blob, in other words, just a sequence of bytes. There are several ways to obtain these bytes. For example, if all your data has the same type, you could store everything in an std vector and pass its contents directly. But that doesn't work very well if your push constants contain different types. For example, a float and a uint, and you want to upload them in a single call. To solve this, I created another helper function called getPushConstantData. It's actually a nice little C++ exercise that demonstrates periodic templates. I know, templates, and especially periodic templates, can look intimidating, but I promise this one is quite simple. The getPushConstantData function accepts a periodic number of arguments and returns a std array of bytes. Since push constants are guaranteed to be at most 128 bytes in Vulkan 1.3, returning an object of that size is perfectly reasonable. It's allocated on the stack, so it should be very efficient. The first thing I do is verify that the total size of push constant data doesn't exceed 128 bytes. To compute the total size, I use a variadic fold expression. Basically, I evaluate size of for every argument and sum the results. Once we know the total size, we create a byte array of exactly that size. Next, for each argument, we call the helper function append push constant data. This function copies the argument into the byte array and updates the current offset. Let's see how this function works. First, it determines the size of the object we are copying. Then it simply uses memcopy to copy the bytes into the destination array. This is how we solve the problem of packing different types, such as float and uint32, into a single block of push constant data. Finally, we increment the offset so that the next argument is copied to the correct position. After processing every argument, the byte array is fully populated, and we simply return it. Now, with everything finally in place, let's build the application and run it. Oh yeah, it works! We finally get the green color, and there are no validation layer warnings anymore. Now you may wonder, okay, I do see some green on the screen, but how do we know that a triangle was actually drawn? To verify this, we can use a graphics debugging tool. There are vendor-specific tools available, but there is one that I simply can't price enough. It's an amazing tool, and I use it all the time whenever I have shader issues or need to debug graphics code. It's called RenderDoc. Here I simply launch the application. To capture a frame, I press F12, then close the application. Now we can inspect the captured frame. In this case, I captured frame 280. Here we can see the first begin rendering operation. This is our render target path. It shows the render targets as the color attachment. If we inspect its parameters, we can see exactly the values we specified when we created it. We also see the clear color, which is our light green color. There is another render path. This is our full screen triangle path. Here, the color attachment is the swap chain image, the final image that will be presented on the screen. We can also see our draw call with 3 vertices. Now let's inspect the pipeline state. If you open the pipeline state view, the part we are interested in is vertex input. When we open the mesh viewer, we can see that there is no vertex input at all. As you remember, we generate the vertices on the fly inside the vertex shader. If we switch to Output tab and enable Highlight Vertices, we can clearly see the generated triangle. This small rectangle in the middle represents the viewport, our window, and this large triangle completely covers it. As you remember, this exactly matches the diagram I showed earlier when I explained how the full screen triangle works. So, as you can see, there is no magic here. Everything behaves exactly as expected. Phew, that was a long video. But we covered a lot of topics. Now we know how to allocate GPU memory, create images, update descriptor sets, create pipelines, and all this other important stuff. We are almost ready to start the really cool part, mesh shaders, right? Unfortunately, no. There are still some things we need to implement before we can get there. For example, as I mentioned, we can create images, but we haven't used any buffers at all yet. And buffers are extremely important in Vulkan. We also still don't know how to transfer data from the CPU to the GPU. For example, how do we take some vertex data created on the CPU and make it available inside a shader? In the next video, we will continue working on this. But instead of just creating abstract Vulkan objects, we will build another small project. We will start drawing a GUI using the famous GUI library. This will help us prepare all the necessary pieces for our final goal. So, stay tuned, take care of yourself and your loved ones.